So it's good to see you, Scott. For me, it's been many years since I've seen you. I visited Hopkins long ago.
Yeah. Oh,
yeah.
We have our invitation list, and you guys are both on it. But I think somebody has to get the nerve up to call you. So it's your phone for the next couple months.
So we want to talk today about your GE paper, Generalized Estimating Equations, which has about 21,000 citations, and it's an important paper in applied statistics. We want to hear from you how it came about, and then maybe the impact it's had, and whatever you want to talk about after that. So
yeah. All right. So it came about, I think, because there were actually 5 junior faculty that were hired into my department, the department I'm still in at Johns Hopkins, and over a 2-year period. And the department was pretty sleepy. It had lost a lot of funding, and it was down to about 7 or 8 faculty. And they got a grant from the Mellon Foundation to hire junior faculty. I hired 5 in 2 years, and we came from very different places. And 2 of us, Kung-Yi Liang and myself, collaborated from the beginning. And I've written papers with all 5 of those faculty. And
how old were you when you wrote that paper?
How old was I?
Yeah.
That's a great question. I was probably 30, something like that, 28 or 30.
Yeah.
And let's see, actually, 1986. So I was 33.
Yeah.
And but Kung-Yi was trained actually a student of somebody Norm Breslow, who was a student of Brad Efron's. Yeah. And Norm was very much a leader at the University of Washington in sort of likelihood-based inference, conditional inference. So Kung-Yi came with a knowledge of generalized linear models and sort of the whole biostatistical milieu of how these models all relate to each other, and if you condition on a Poisson, you get all that sort of stuff. And I came from a department at Princeton where I worked on time series analysis, or frequency domain time series analysis. So I knew about correlated data, and but not very much about discrete data. In fact, I remember John Tukey making a comment in one of the lectures when he was asked about the sort of binary outcomes or binary data. He made some sort of comment that if you're working with scientists or collecting binary data, you probably should find new colleagues, because
I think he was a bit off on that one.
Yeah. Well, so somebody asked him, well, what about death? Yeah. He said, well, yes, there's some binary variables that are very important, but often they're just bad. They're sort of secondary measurements on things that should be made continuous. But so anyway, that was my training, and I never had any exposure to anything categorical data, any sort of that problem. And then when I came here, started just finding all kinds of interesting research data sets and collaborators who were interested in statistical input, and all the data was discrete, and so I started learning about that. And anyway, between Kung-Yi's interest in discrete data models and my interest in correlation, we sort of found this problem to work on together. And we worked with Steve Self. Somebody you may not.
Yeah, no.
Yeah, he was also a University of Washington graduate, and he was in one of those junior faculty. And the 3 of us wrote a paper about sort of Markov chain models for repeated binary data, and then Kung-Yi and I went on to think about the generalized linear model family. And if you guys remember, I learned about generalized linear models on a short visit to England in 1985. And it was the GLIM.
Oh, that was it. Were we were there too?
You were both there, I'm pretty sure. I remember.
It was in Lancaster, is that right?
Lancaster, England.
Yeah.
Exactly.
Yes.
Yeah, and what I remember about the conference is that many people called it the GRIM conference, not the GLIM conference. But I remember there were sort of a competition between the Stanford people who gave talks, and then somebody from the generalized linear model world in England gave a talk, and each of the talks sort of subsumed the one that came before it. And it's like, that's a special case of what I'm about to talk about. The next one said that's a special case. And so there were these dueling special cases. And
that's right.
I remember that. Peter Green was in the fray, I think.
Peter Green was a key player. And basically the conference, most of the talks, not the ones I just mentioned, but many of them were about how to do every possible analysis in the software package GLIM, which wasn't very easy to do. But
yes, exactly. All the tricks you could fit survival models in GLIM, and there were all kinds of tricks you could pull to.
So at that point, you hadn't written a GE paper, is that right? Did you talk about
no. We were working on this general question about how to do, that we were sort of trying to build strength in a department, and one of the strongest departments in our area was at Harvard, and Nan Laird and Tom Lewis and others there were working on longitudinal data analysis, mainly with random effects models.
Yeah.
And so we I remember went to a conference there, and maybe in 1984 or 1983, and sort of saw what they were doing. They were doing mostly continuous data, and we were then interested in trying to think about generalized linear models and how to extend them to the case of longitudinal or time series data. So that was the motivation. We had lots of data sets like that here. And so, and we were strongly influenced by, Peter McCullough's book, John Nelder and Peter McCullough's book. I think we saw it in an advanced copy. And so the quasi-likelihood idea was around. And actually in my training at Princeton, we talked a lot about estimating functions, only because, all the robustness work that you guys are familiar with, the Princeton robustness conferences, that all was happening when I was a graduate student.
Who's your advisor at Princeton?
So I work for Peter Bloomfield.
Oh yeah, Peter Bloomfield, time series guy.
He was a time series, and actually it was a very interesting department. There were three professors, John Tukey, Jeff Watson, and Peter Bloomfield. Peter was like 28 when he became a professor. He was sort of a wunderkind, and he was the other two were challenging to work with, and so I know you guys are close to Yoav Benjamini. He was also Peter's student at the time.
I see. Then that department blew up at one point. Like it's gone.
Yes. Right? So actually, it closed probably 5 or 6 years after we graduated. Yeah. It was created as a department because John Tukey was such a big influence in the university, and then he retired, and they had a lot of internal squabbles in that department. He and Jeff Watson were, they were good colleagues, I guess, but they had different points of view, and they were often squabbling. And I think the deans felt like there was only 3 full professors, and if you had to cut back, that would be a good place to start. They had great department. I mean, David Donahoe was an undergraduate, and Joe Romano was an undergraduate then, and Nate.
Silver?
No, not Nate Silver.
Daryl Pregamon. I think Daryl Pregamon was a postdoc.
Daryl Pregamon was a postdoc there when I was there, and it was a great, very small, maybe 7 or 8 graduate students, but some great, and Yoav and Alan Wilkes. You guys may know Alan Wilkes. He was
sure. No, we know. Oh yeah, for sure.
Yeah,
I was at Bell Labs with him. So Scott, getting back to GEE. There's a contrast between GEE and GLMMs, right? Generalized linear mixed model. And it's a different approach. Can you just say something about that?
Yeah, so generalized linear mixed models are extensions of generalized linear models, but that you get by adding random effects. And in the more nonlinear models, like the logistic model, if you add linear effects on the random effects on the transform scale, on the natural scale, then you hit them with a nonlinear transformation to go back to the data scale, and the mixing nonlinear functions tends to produce things that aren't directly related. Well, they're directly related, but they're not what you'd expect them to be. There's like a sort of a smearing that goes on, and so if you're trying to estimate like the prevalence of a binary outcome as a function of covariates, and when I say prevalence, I mean like the population rate as a function of covariates, and somebody else is interested in modeling an individual's risk as a function of covariates. The prevalence is obviously the average of the risks, but if you transform to in a nonlinear way, you don't get that the model that you do on the risk scale, the parameters don't have direct interpretations on the frequency scale or population scale. So it's not a big thing, but it's, you have to keep track of this. And there was, and the other thing I'd say just before I leave that idea is that if you build random effects models on the transform scale and the linear predictor scale, then those things are not directly estimable. And most, if you think about just trying to estimate it from one person's data, you have to have a lot of measurements to be able to estimate a time series model, a binary time series model. And so you don't get very much information about the random effects for any one person. And so there's a lot of shrinkage that goes on when you estimate those sorts of models and try to. So anyway, the marginal models tend to be of perhaps more interest in the public health space, where you're interested in population rates of things, and the random effects models more interest perhaps if you're a clinician trying to say what this patient's risk is. Yeah. But they're not directly comparable the way they are on a linear model.
Now, you did a lot of work in air pollution with Francesca Dominici and others. Did you use GE a lot in those analyses?
Some, but those problems actually, the predictors were mainly continuous, and the outcomes were mainly continuous because we didn't ever have, and most of the work I did, we almost never had individual data. We always had community data. So we fit mainly log linear models, right? So, you know, you think of Poisson regressions with random effects for cities and time and so forth. And they're the connection between the models on the linear scale, on the transform scale, and the models for the population rates are more tightly connected to each other, and you can do one or the other. So
the other advance in GE is that you allowed a working covariance, right? You can move away from the normal, and it's more non-parametric, more, right?
Yeah. So if you think about correlated data, you know, the multivariate Gaussian is sort of the natural model that is easy to model correlation and the mean and the correlation, and they're separable. You know, they're sort of asymptotically orthogonal to each other, and so there's lots of nice properties using the multivariate Gaussian. When you go to like multivariate binary or multivariate count or multivariate other kinds of, you know, skewed data, then the covariance structure and the mean structure are more tightly connected to each other. So when you want to build a model of both the means and the covariances, easy to do in the linear model, but more challenging in the nonlinear model. And in fact, simple kinds of things you might assume about covariances, you know, are they don't naturally transform to the nonlinear, to logistic models, for example. So these models, which we typically use, like exchangeable correlation or, you know, autoregressive correlation, things like that, they're only approximations to what's happening if the outcomes are binary, because, you know, there are constraints on the correlations that have to do with the means and all kinds of complications. So to not have to, you know, spend too much concern about that, the estimating functions that you have for the mean parameters are still unbiased, even if you've got the wrong correlation structure, if it's an approximation to the right one. And so, you know, that got us, and that comes again from this interest in estimating functions. There's sort of a long history. It goes back to Peter Huber, and even before then, you know, papers that look at the properties of maximum likelihood estimation when the model's wrong. And those ideas just carried right over to the GEE problem.
So when you submitted the paper, did they say, yes, wonderful, publish as is, or I'm asking that because some students be watching this, and they often have that, you know, it's easy to publish, and anyway.
Yeah. Well, so I think let me tell that story quickly. When it was 1985 again, when we went to the GRIM conference, we Kung-Yi and I took a mini sabbatical in London, and we actually took it at Imperial College, and we had submitted the paper to Biometrica, and Imperial College was chaired then by the editor of the Biometric, David Cox.
I've heard
And so
of
we got to know David Cox pretty well because at Imperial College, he got to work around 8 o'clock every morning, as did we, because that was just the tradition, the sort of the US tradition, and the rest of the staff tended to come in around 10 or 11. And so, you know, there was only the three of us in the department. So we got to know him, and the paper was pending during that time. And fortunately, he took pity on us and published it. So anyway,
he pretty much made decisions, right? He did.
Yeah.
I remember submitting one paper there, and it got to him. He got rejected. But not only that, he took the time to change all my. You know, they have parentheses rules. Remember that? There was by hand. He went through it.
And we did all.
They rejected it.
Well, I think he was encouraging you, Rob.
I see.
He did all the editing on the train to and from home, and so if he was reading it, he fixed it on the way, and then he made his decision when he got to work.
I should be honored that he would fix my parentheses. Is that what you're saying?
Anyway, Scott, it's a great paper. It's had a big influence, and it's really nice to hear firsthand from you how it happened. And it's been wonderful chatting.
Yeah, it's great.
So we're gonna
thanks for taking some time, and appreciate to see you both looking so well.
Yeah,
you too.
And don't go.